Hello friends, in the present video, which is in continuation of the first video on factor analysis. In the first video, we tried to understand the basic of factor analysis, what it is actually, when we are going for factor analysis, what is its importance. So in the continuation of that first video, in the last part of that video, I have talked about the steps of factor analysis. So in the continuation of the first video, in this second video, I will be discussing the steps in detail. So while discussing the steps in detail, I will be also talking about different key terms related to factor analysis like eigenvalue, like correlational matrix, like commonalities, like scree plots. So we will try to understand these key terms also. And once we understand these key terms, we will be in the better position to understand what is factor analysis, what are its different types, how we are going to use it, what is it, what are its uses in social sciences or in research, in education or behavioral sciences. So let us start. So let us revisit the steps in factor analysis. In the first step, we try to see what are the objectives of our problem. Are we going to explore factors, or we are going to confirm with a particular model of it? So based on that one, first we decide on what is our objectives. Are we are going to develop a questionnaire, or we are just going to collect data based on certain variables, and then we try to see what are the underlying factors in it. So what are our objectives? What is the objectives of the problems that we try to understand? And based on that, we decide that we have to go for CFA or EFA, that is confirmatory factor analysis or exploratory factor analysis. So if the relationship among the item is not known, then we are going for exploratory factor analysis. But if there is certain type of relationship that we already know, and we are just trying to confirm with that set of relationship with the data collected from the real field, then we have to go for confirmatory factor analysis. CFA or confirmatory factor analysis allows the researcher to test the hypothesis that a relationship between the observed variables and the underlying constraints exist or not, or if it is conforming to a SEM or sequential equation modeling. So established SEM is there, just we try to confirm with that particular relationship, if it is there or not, if it is conforming to that relationship or not, or if you are able to get a new model, or if you are going to go revise that model. So that is, if that is the objective of our study, then we are going for confirmatory factor analysis, else we are going for exploratory factor analysis. So exploratory factor analysis is the popular way of doing factor analysis maximum of the times when the researchers are going to the field to collect data to get the variable. They are basically going for exploratory factor analysis. Once they are getting the variables from the fields which are observable from that sources, if you are getting the variables, then by doing exploratory factor analysis, we can find out the factors underlying in those factors working underlying those variables, which is not commonly visible or which cannot be observed directly. So exploratory factor analysis tries to give you certain factors, certain relationship between the variables. So that is the popular way of doing factor analysis. So we go for exploratory factor analysis, and whenever we are developing a tool also, at that time also, we starting from the very beginning, a new set of variables if you are collecting and you are trying to develop a tool, trying to reduce the variables or reduce the items which we have developed in our variable, so that only the relevant variables will be there in our tool. At that time also, we can go for exploratory factor analysis. So in the next stage, after deciding on which type of factor analysis we are going to perform, either it is exploratory factor analysis or it is confirmatory factor analysis, we proceed for the second stage. So before going further, we should try to test the different assumptions which should be seen in the collected data or collected set of variable or observed set of variable. If it holds or not, then only we can go for exploratory factor analysis. So the first condition for performing factor analysis is that we should test the normality of the observed data set. So we have to see that if the data is normally distributed or not. So if the sample from which we have collected the data has to be normally distributed. Secondly, we should also go for seeing that the variables under investigation should be linear in nature, and the conditions related to homozydicity should be also checked. So basically, homozydicity, as I already told you, that it is not an essential conditions for doing exploratory factor analysis, because whenever we are going for exploratory factor analysis, we are quite sure that we will get number of factors which will be orthogonal from each other, which will be independent from each other. So it is not required that the variance among those variables, that particular group of variables yielding a particular factors, should be equal in with respect to other variables also, other set of variables also. So homozydicity is not an essential condition, because we try to get that particular concept or that particular variable in terms of linear combination of those factors. So those factors are independent from each other, and many a times we are getting number of factors in an exploratory factor analysis. So homozydicity is not an essential condition. It is only essential condition when we are quite sure that only one factor is there. Then only we should see that the variance among that set of variable is equal. Again, we have to see in the next condition, we have to see that the sample is an homogeneous sample. From where we have collected the data should be homogeneous in nature, and the conceptual linkages should be there among the variables. So whatever variables we are taking under consideration for factor analysis, they should be conceptually linked. So sample should be homogeneous, and we should also see that there should be conceptual linkages between the variables. So we test the condition of normality, we test the condition of linearity. We also see that if it is the sample is from where the data is collected is homogeneous or not, and we see that there is conceptual linkages between the set of variables. So this is the second stage of performing factor analysis. So after going with the step 1 and 2, we will go to next step, that is step 3. And first here we decide on which type of factor analysis we are going to perform. So if we are going for exploratory factor analysis, or if we are going for confirmatory factor analysis. Basically here I am trying to talk about which type of factor analysis is in connection of what is our approach towards understanding the relationship among the variables. So there are basically two types of factor analysis approaches. One is Q type of approach and the other is R type of approach. So in Q type of approach, basically we try to see the pattern on the respondent behavior. If there is a cluster formation among the respondents, what they perceive, what they believe about the certain set of variable based on their responses. So it tries to understand the measured dimensions or types of people based on their responses, how they perceive the variable. So basically we try to see their people group formation in relation to that particular variables. So it is called as Q type of factor analysis. Basically Q type of factor analysis try to see the correlation between the subjects, the respondents. That correlations is tried to study. But the normal type of factor analysis, or most common type of factor analysis, is the R type, where we try to see the relationship among the variables under investigation. So basically we decide which type of factor analysis approach we have to follow. We have to go for Q type approach, or if we are going to use the R type of approach. So in the R type of factor analysis, we try to construct a correlational matrix based on the correlation between the variables under investigation, and then we try to observe that particular correlational matrix and just try to see that which type of variables can be clubbed together and underlying factors can be generated. So that is the basic R type of factor analysis. So we decide on which type of factor analysis we have to perform. And generally we used to go for R type of factor analysis. Next, we just try to see that other assumptions of factor analysis are met or not. So we just try to see what is the nature of variable under investigation. That is, we just try to see that the data which is collected should be in metric nature. It should be collected in ratio scale or interval scale. Then we have to go for KMO tests, which is done for testing the adequacy of the sample. That is, if the variable under investigation, if it is sufficient enough to yield us different factors, if we can get certain factors from that set of variables. So it just tests the adequacy of the sample of variables which are under investigation. So we have to go for KMO test. So I already told you that the KMO test value ranges from 0 to 1. And if the value is very close to 1, then it is the best possible chances that we will get specific number of factors which explain the underlying structure between the variables. So if the KMO test value is very close to 1, it is 0.9 or 0.8 above, then there is best possible chance factor analysis will yield certain result. Basically, in generally, if we go for factor analysis and then we go for KMO test, many a times if the value is more than 0.5, then only technically we can go further and go for performing factor analysis. If the KMO test value is more than 0.5, then we proceed further. We try to go for rotation, and then you try to see the different factors emerging from those set of variables. So technically, if it is more than 0.5, you can proceed further and do the factor analysis, further steps of factor analysis to determine the factors from those set of variables, or we can say that we are able to extract factors from those set of variables. So it is a technical, or you can say that the benchmark statement or the cutoff point, that if it is more than 0.5, we can go further and do further steps in factor analysis. But if it is less than 0.5, we should not go for factor analysis. That says that the sample or that variables which we have for which we are going to perform factor analysis, they are not sufficient, and we have to see that if we can have more number of variables from which we can go for which will yield certain factors, and which the factors will be significant also. But the best chances are there if it is very close to 1. So 0.9, 0.8 is the best values yielded by KMO test or Kaiser-Meyer-Olkin test. So if the value is very close to 1, then we are done, and we can go for further steps in factor analysis. Again, the second factor, it is here we are talking about the sample from which we are collecting the data, that the number of respondents. So it is written in different resources or books that the sample size from where we are getting the data should be 3 to 5 times the number of variable under investigation. So it can range from 50 to 100 to 1000, but basically I will suggest that we should go for at least 100 number of samples. From 100 subjects we should collect data, and then only we can minimize the error variances. After that, we go for constructing correlational matrix, and here it is also an preconditions before we go for further steps in factor analysis. We go for performing Bartlett's test of sphericity. Now, what is Bartlett's test of sphericity? Bartlett's test of sphericity starts with an hypothesis that our correlational matrix is an identity matrix. So So it starts with a null hypothesis that our correlational matrix is an identity matrix that says that there is no relationship in between the variables. So if the null hypothesis holds or a null hypothesis is accepted, then we cannot perform factor analysis and we should not go for further investigation because we already got the result that there is no relationship or no significant relationship between the variables. So there is condition of singularity among the variables. So if Bartlett's test of hypothesis, if it is tested and the test result is found significant, that is our null hypothesis is not accepted and we get the alternative hypothesis right, that is it is not an identity matrix, we can go for further steps in factor analysis. So our Bartlett test should be significant, the value should be less than 0.05, then only we can go for further steps in factor analysis. Now should not confuse with Bartlett's test of sphericity with Bartlett's test of equality of variance. There is other test of Bartlett which is Bartlett's test of equality of variance. So it is done to test the equality of variances, and that is not commonly used because whenever we are sure about that there is a unifactor model or among the variable there is only one factor is involved, then we go for performing Bartlett's test of equality of variance, and that test result should be obtained, and then to test that there is equality of variance or not, and then we go for further steps in factor analysis. But most commonly in factor analysis, or most preferably exploratory factor analysis, there are multiple factors involved, so equality of variance test is not required here. We go for Bartlett's test of sphericity. I hope you understood what is KMO test. KMO test value should be closer to 1, and for Bartlett's test of sphericity it should be significant, and then only if these two tests are passed then we can go for further steps in factor analysis. We can see the pattern among the variables, we can go for finding out the commonalities, we can go for finding out the factors, we can go for rotating the factors and extracting the factors. So now we will go further and understand different other terms related to factor analysis so that we can understand the remaining steps of factor analysis. So first we will try to understand different other terms related to factor analysis. Some other terms are there. So if you will understand them, then only we can go for performing factor analysis, either if you are doing it manually or if you are doing it using SPSS or R software. If you will understand those terms only, then only you can proceed. So let us see. Okay, whenever we are going to do factor analysis, we are trying to study the variable or different set of variables. So we collect data on different set of variables and we just try to see if these variables can be clubbed together or different set of variables can be clubbed together to yield you certain factors so that the variables or the number of variables can be reduced. So basically we are trying to utilize their variance, the variance of those variables, and just try to see that if this variance can be shared among themselves, among certain set of variables so that they can be clubbed. Let us try to understand. So whenever we are going to do factor analysis on the set of variables, we basically try to identify the variance related to that one f, and if these variance are shared variance. Okay, let us try to understand. So let us see this particular variable. In a particular variable there is certain variance which is specific to that particular variable, or we can say that it is unique to the variable itself. It is not shared with other variables. So it is the unique variance which is specific to that variable. Again, there is other variance which is called as common variance, and that common variance, that variables may share with other variables. We can see variance which it shares with other variables in a matrix. So if you are trying to observe certain underlying factors or underlying relationship among the variables, it is because of this common variance only we are able to identify those latent relationship. So let us try to understand. Suppose we are trying to study the personality of an individual. Okay, so if our holistic objective is to assess the personality of an individual, now we know that the person attitude is one of the variable or one of the concept which is somehow related to his personality. So in that particular question here, some items or some variables will be related to person attitude. Now whenever we are measuring attitude, some of the variance related to those items will be very unique to a person attitude only, that it will determine a person attitude only, which is called a specific variance, which is unique to his attitude only. But there may be certain amount of variance which it may share, that attitude can share with some other variable, like the person's self-confidence. Suppose self-confidence is one variable on which you have prepared certain questions whenever you are determining the personality of that particular person. So on self-confidence, certain questions are there. So that common variance which is there in on that particular person's attitude, it may share with the common variance of person's self-confidence, and they can together determine the personality of that particular individual. So this is actually what is going behind whenever we are performing factor analysis. Because of this common variance only, we are able to get the underlying factors or underlying relationship or latent relationship. So we have got a specific variance related to the variable, we have got common variance related to the variable, and there are some chances of error variance also, which may arise due to measurement error or some random error due to respondent's behavior or some other instrumental error. So error variance is also there. So let us take one example. In this particular diagram, in this particular diagram, you have got variable y1, y2, y3, y4, y5, and through it you have got factors f1 and f2. And these factors we have got because there is certain amount of common variance among these variables. So because of this common variance, we are able to club them and we are able to generate certain factors. So this is the main theory or main idea working behind factor analysis. Okay, after understanding the variable and the variance which we use while performing factor analysis, now let us understand what are the different approaches of factoring. So there are many approaches towards factoring. What basically is the approach of factoring means that in which way we try to extract the factors from the set of variables. What actually is the meaning of approaches of factor analysis or approaches of factoring? Basically, we try to see that in which way we try to extract the factors by observing the correlation among them, among the variables. What will be our approach? Which type of variance or share variance which we are going to use while extracting the factors? So there are several approaches of factoring, like principal component analysis, common factor analysis, image factoring, canonical factor analysis, alpha factoring, factor regression model. There are several other methods also, but the most common are principal component analysis and common factor analysis. And it is also there that principal component analysis is mostly used. So basically, whenever we are going to do factor analysis, PCA or principal component analysis is mostly used. So we will be discussing about PCA and CFA in later part. Let us understand this different other approaches to factor analysis in little brief. Like canonical factor analysis. Canonical factor analysis tries to get the factors based on canonical correlation among the observed variables. Then image factoring tries to get the factors based on predicted variables and not on the basis of observed variables. So it tries to get the factors based on predicted variables. That's why it is called image factoring. That is, it is not taking the observed variable from the field. It is trying to get the factors from the predicted set of variables. So in image factoring, we go for extracting factors based on the correlational matrix which is made from the set of predicted variable, not from the set of observed variable. We try to use the predicted variable. Alpha factoring is based on maximizing the reliability of the factors, and factor regression model, from the name itself it is quite obvious that it is a hybrid model. We just try to combine factor model and regression model to get an hybrid model. Including these methods, there are several other methods also there for approaching factoring, that is least square method, that is generalized least square method, maximum likelihood method. So there are several other approaches, but basically we will be concentrating on principal component analysis and common factor analysis. Okay, let us first see in detail what is principal component analysis. So PCA, or principal component analysis, seeks a linear combination of variables such that the maximum variance, just you try to see, the maximum variance is extracted from the variables. It then removes this variance, so that variance is removed, and then we go for the second iteration. We seek a second linear combination which explains the maximum proportion of the remaining variance, and so on. So this is the process in principal component analysis. We go to extract the maximum variance first, then we go for the second step where we again try to segregate the variables based on their maximum variance. So PCA tries to get an unique solution so that the original data can be reconstructed from the results. It looks at the total variance among the variables. That is, it takes care of the unique variance as well as common variance. So common variance it also use, and that specific or some amount of unique variance which is there in those set of variables, that also it uses. And then in this method, the factor explaining the maximum variances is extracted first. So in principal component analysis, we consider common variance as well as unique variance. And of course, sometimes the error variance also. And thus the factors which is responsible for explaining the maximum variance is extracted first. And in the same manner, we proceed further to extract the remaining factors. So this is called as principal component analysis. The next approach of factor analysis or factoring is common factor analysis or principal factor analysis. If we assume or wish to test a theoretical model of latent factors causing observed variables, it is known as principal axis factoring or principal factor analysis or common factor analysis. So in this, we try to get the least number of factors which account for common variance. The primary aspect of factor analysis or common factor analysis is to unearth the latent or which are not observable directly, which are underlying, we get those factors. Primary objective of common factor analysis is to get the latent factors which are most important and are accountable for common variance. So basically in principal component analysis, it proceeds from some deterministic factors which are already there, and then we try to develop a linear combination of factors based on the total variance or maximum variance. But in common factor analysis, we try to get the factors which are underlying, which are latent. So in that, we try to move backward from the latent variable set of variable. We try to get the factors which will in turn give you the variable under investigation. Again, the difference is there that in common factor analysis, we are talking about only the common variance. So in the common factor analysis, we are talking about only the common variance. We are not taking care about the shared variance. So that is also one of the main difference among common factor analysis and principal component analysis. Basically, you can also understand that the first one is called as principal component analysis. That means we are trying to get the component. There the name factor is not there. So there we are just trying to reduce the number of variables, so that whenever the intention is there that we have to reduce the number of variables under certain component which yield maximum variance, then we go for principal component analysis. But whenever our objective is to study the underlying factors, or we want to extract factors, we should go for component factor analysis. So both of them both are equally used whenever we are going for factor analysis, and we decide upon our study objective, our context of investigation, and we decide if we have to use principal component analysis or CFA common factor analysis. You can also understand the difference between principal component analysis and common factor analysis seeing this diagram. You can see that in this particular diagram, these components are derived from the items, which are linear combination of item scores that you can see here, and PC analysis moves forward based on direct linear combination of item scores. But in common factor analysis, we first try to get the factors. So item score is linear combination of factors plus the item's unique variance. So you just try to see, because it is based on common variance only, so you get the factors based on common variance, and thus the item scores are based on factors and their unique variance. So CFA analysis moves backward from the item score to determine the underlying latent hypothetical factors, which are represented by dotted line here. So you can understand. So basically, if our main intention is to reduce the number of variables or lessen the number of variables, or if you are trying to get the components, that's why it is called principal component analysis, then we go for performing PCA. But if our purpose is to get the underlying factors which are arising due to common variance shared by the variables, then we should go for common factor analysis or principal factor analysis. If we are saying we are going for principal factor analysis or principal axis factoring. So it depends what is our objective, but both of these methods, CFA and PCA, both are mostly used whenever we are going for factor analysis. So if you have performed factor analysis using SPSS, you will get this option to choose in between different types of factoring method, and mostly we go for PCA, or you also choose component factor analysis also. So both the methods you can use. Now the next term which is related to factor analysis is correlational matrix. So you just see whenever we are going to perform factor analysis, we construct a correlational matrix to study the correlation in between the variables. So you can see this particular correlational matrix, you can just see. So there are certain set of variables q1, q2, q1 to q6, and then again horizontally you can also see q1 to q6, and it is trying to understand different type of correlation among the variables. So it is constructed to analyze the pattern of correlation between the variables. It tries to see which variables tends to be highly correlated. You can see here this particular correlational values 0.987, which is in between q1 and q2. It is highly correlated. It also tries to see which variables can be clubbed together. If the variable which are highly correlated, likely that they represent the same underlying dimension, means if they are correlated with each other, if there is certain error variance involved, or if certain more rotation is required. So basically we try to see the correlational matrix and try to understand the correlation in between the variables. Factor analysis pinpoints the clusters of high correlation between variables, and for each cluster it will assign a factor. So there will be different, because several factors are there we are extracting for factor analysis. So in that correlational matrix, it will try to see the different clusters of correlations, different groups of correlation, and for that particular clusters, those variables which are responsible, they can be clubbed and a factor can be generated. So this is correlational matrix. Next, we can see next key term is factor loading. So what is factor loading? Factor loading, which is also called as component loading in PCA, are the correlational coefficient between the variables rows and factors columns. We will try to understand that with a diagram or with an example. So it is basically the correlation coefficient between the variables. So variables under investigation, there may be several variables, and the component which are extracted, or the factors which are extracted. So which variable is loading to which factor? It is one type of coefficient or one value which we can see, or we can understand that which variables are loading most to a particular factor. That means it is, in one sense, you can understand which variables are mostly responsible for determining a factor. It means that the variables may be loading to several factors. Suppose we have got 2-3 factors, and the variables may be loading to different factors, but to which factor it is loading most. So by seeing the correlation coefficient, the value of that correlation coefficient, we can understand that that particular variable or set of variable is determining which factor. So square factor loading is the percentage of variance in that indicator variable explained by that particular factor. So if that factor is responsible for which amount of variance in that particular set of variable. Let us see this example. We just see this is the variables. You can see it is in this column, the variables are there, and here 3 different factors, or you can say 3 components are there. This is component 1, then component 2, and then component 3. Now you can understand that this variable 1, the factor loading is minus 0.198. Similarly, for this variable 1, factor loading for component 2 is minus 0.805. And for component 3, the factor loading is 0.061. So you can say that these particular factors is mostly responsible for this variable variance, or you can say that this variable mostly variance in this variable is maximally explained by this particular component or this factor. So these are the factor loadings. This is 0.173 is also one factor loading. Then all these are factor loadings, and you can see that for component 1, the factor loading is maximum in case of variable 8 and variable 9, minus 0.792 and 0.792. Irrespective of the sign, you can see that the variance responsible in variable 8 is maximally represented by component 1. And similarly for variable 9, the maximum variance is being explained by component 1. So for variable 1, you can see that component 2 will be the significant factor, and so this set of variables can be clubbed together to give this component 2, or you can say that variable 8, variable 9 can be clubbed together. Similarly, the variable 1, variable 2 can be clubbed together to give component 2, and similarly component 3 also, you can see that the variables like variable 3, variable 4, variable 3 and 4, those can be clubbed together. So this is one impression of what actually is factor analysis. You just try to extract these components and we can name those components separately, and that's why for this number of variables, suppose we have got 9 number of variables, we get only 3 factors. So in these 3 factors or these 3 components will entirely represent these all 9 variables. So that's why factor analysis is one type of variable reduction technique. Now come to the next key term. The next key term is the communality. So what is communality? The sum of the squared factor loadings for all factors for a given variable in a row is the variance in that variable accounted for by all the factors. So what is communality? The communality is the sum of the squared factor loadings for all factors for a given variable is the variance in that variable accounted for by all the factors. So I already told what is factor loading. So if you square it, then it becomes the variance. So communality is for a particular variable in a row, the addition of the square term of factor loadings across different factors will give the communality. You will understand when you will see that one example, you will understand. You can also see the communality measures the percent of variance in a given variable explained by all the factors jointly. So previously I told you that these factor loadings are one type of measure or one type of variance which explains a given variable or given set of variables. Now communality, you can say that it jointly represents the total percentage of variance explained by all the factors taken together for a certain variable, and may be interpreted as the indicator of reliability of the variable. So it also indicates the reliability of the variable. Suppose the communality, if you add percentage of variance explained by that particular number of factors, if you get a particular percentage, you can also always say that particular variable is reliable or it can be taken into consideration for that particular variable can be taken into consideration in determining that the model. Now there are different cutoffs. There is cutoff for the deciding on factor loadings also. There is cutoff for deciding on communality. So it depends upon our study objective, the context of our study. For factor loading, basically we go for taking factor loadings 0.4 and above. Sometimes if you are more some stricter condition, you can also go for 0.7 and above, but it may be plus or plus minus, but 0.4 and above, it can be taken into consideration. Similarly for communality also, it should be 70% and above, then it is very good. But we also take into consideration if it is 40% above, or 0.4 or 0.5 if it is coming, that is the correlation value. But if you convert into percentage squared, that is the variance value, common variance value, means when you add the squared of variance or squared of factor loading for a particular variable across different factors for a set of variable, it is 0.4 and above. You can always go for further steps in factor analysis or factoring. So let us understand what is communality with this particular example. Now you can see in this particular example, you can see that these are the variables and these are the different component or factors, component 1, component 3. Now you can see that what is communality. You can always see this is the communality 0.690, 0.69095, 0.687566. And how we have got that one communality of variable 2. Suppose for this variable, if you are trying to get the communality, it will be the square of this particular term, then is plus square of this plus square of this. So if you get the square of these three components of factor loadings, then you will get the commonality as 0.68, and in percentage it is represented here 69%. So you can say that the 69% of the variance in variable 2 is represented by these three factors, can be determined by these three factors. If this value is very low, then these variables should not be considered for our investigation. So I already told the benchmark is 0.4 and above or 40%, but maximum of times you should go 60 and above 60. And if it is close to 70 and above, then it is the best situation for doing factor analysis and extracting the factors. Okay, now the next key term is the eigenvalue. So the eigenvalue for a given factor measures the variance in all the variables which is accounted by that factor. So it is quite different from commonality. Here we just try to see that factor, how much it is capable of explaining the variance among all the variables. It is the amount of variance explained by a factor. It is also called characteristic root. So in turn, the eigenvalue is in a way a measure to understand to how much extent a particular factor is explaining the observed set of variables. So if it is significant enough to explain the observed set of variable or not. So eigenvalues represent the total amount of variance that can be explained by a given principal component, because factors are also called as component. So we can say that how much that particular factor or component explaining the entire set of variables. In turn, it is a measure to assess that how effective the factors are in measuring the construct under investigation or the concept under investigation. So if you are reducing the variable to certain factors, if it is capable of measuring that particular concept under investigation or not. So let us understand this particular eigenvalue with this example. You can again see the same example. These are the set of 9 variables and we have got these 3 factors or component. So you already know what is commonality. Commonality we have already understood. This is something obtained from these 3 components. If you square these terms, if you are squaring these terms and adding up, then you will get this commonality. But eigenvalue is based on this particular values. So across the component means for a specific component, if the factor scores means, so for a particular component, if you will take this factor loading under consideration, you can see here. So eigenvalue for component 1 for this particular factor or component, if you square all the factor loadings minus 0.198 square and all this, then you add it and you will get a value of 3.36. So eigenvalue you have got 3.36. So this is the eigenvalue, and to get the amount of variance explained by that particular factor for the given set of variable, you can use this formula: proportion of variance explained by factor 1 or component 1 equal to eigenvalue divided by number of variables. So in this particular case, you have got 3.36 and number of variables is 9. So if you divide it by 9, you will get a value of 0.373. And if you convert into percentage, you will get 37.3. So this particular component or factor is explaining 37.3% variance for this entire construct or the entire set of variable. Now again you have to understand that what is the benchmark for deciding on which eigenvalue we have to consider. Ideally, the eigenvalues above 1, that is, here it is 3 point something, here it is 1.6, here it is 1. So these three components can be considered. So the eigenvalues above 1 are taken into consideration, and the values having eigenvalue below 1, they are not understood to be found significant enough to describe the set of variables. That's why they should not be taken into consideration. So the percentage of variance, if you can say, explained by these three set of component, three set of variable, if you can see it, you can get that 37.3, 10.6 and 11.3. So if you take the percentage of variance explained by all these three factors for this particular study, if you'll see, you can say that it is coming up as 65 or 70, 65 to 17, between 65 to 70. If you'll add 37.3, 18.6 and 11.3, it will come in between 65 and 70. So they are quite considerable. They can be considered as component of this particular study, this particular set of variables. Now the next term is factor scores. So we have got the idea of what is factor loading, we have got the idea of what is eigenvalue, we have got the idea of what is commonality. Now the next term is factor scores. So factor scores, which is also termed as component score, are the score of each cases row on each factor. To compute the factor score for a given case for a given factor, one takes the case standardized score on each variable and multiplies it by the corresponding factor loadings of the variables for the given factor. You can read it out, whatever things are there. So you have to first obtain certain standard score and then you multiply with the factor loading. So it is very much related with the factor loadings. Every term, the commonality, this eigenvalue, so everything is related with the factor loadings also only. So here first we have to obtain the standard score. So standard scores you can only obtain if you are doing factor analysis by using SPSS. We will get the standard scores and then we multiply with the factor factor loadings, you will get the factor score. It is one, in one sense you can again understand it is the weight of each factors for every variable. Factor loadings are also one type of giving, it is a weightage of every factor on every factor, every set, every variable or set of variable. Factor scores are also one type of standardized scores, just like if you can understand, if you can say that if it is Z scores is there, if that Z score is converted into, if suppose the raw scores are there and you can convert it into Z score, some standard score. Similarly, the factor scores are one type of standard scores for factor loadings, and that can be done when you are using that can be easily done when you are using SPSS or some software package for doing analysis. Manually it will be taking time and it is quite lengthy. The next term under factor analysis is the scree plot. Now what is a scree plot? Whenever you are doing factor analysis, whenever you will use a software package and you give the option of scree plot, you will get a graph which is plotted using the eigenvalues. So you will get the eigenvalues and then you will get the factors. So these two particular things will be shown in that particular graph. You can see the graph. So in one axis you can see the eigenvalues, in the other axis you can see the component or factors. So it is basically gives us a visual representation of variance associated with each factor. The steep slope shows the large factors and the gradual trailing off shows the lower factors lower than the eigenvalue of 1. You can see in this particular graph, these all components, these are having eigenvalue more than 1, and this is quite steep slope. And here you can see an elbow. It is also called elbow. So basically by studying this scree plot also, you can see that there how many factors we can extract from a set of variables. So here those values which are more than 1, 2, 3, 4. So 4 factors we can extract from here. Okay, so in the different methods of factor analysis, basically we just try to get a set of factors extracted from a data set. And it is also that the extracted factors are orthogonal to each other. And basically we just try to extract few factors which are quite significant and they are responsible for the entire variance or for most of the variance of that particular variables under investigation. Basically, in different type of factor analysis, we try to extract specific number of factors which are capable of explaining most of the variance, if not possible 100%, most of the variance in the data set. So, and it is also there that the factors which we are extracting are orthogonal to each other, independent from each other. Basically, we try to extract very few factors which are important one, reliable one, and are explaining most of the variance of that entire variable set. The other factors are treated as not significant, or they are producing lots of noise in that particular data set, or they should be discarded. Generally, in the factor analysis process, once we extract these factors, this significant number of factors, we go for rotation of the factors. And these rotations are generally of two types. One is orthogonal, you can see one is orthogonal and the other one is oblique type. So what is orthogonal type of rotation? Whenever we take it that the rotated factors will be orthogonal from each other, then it is called as orthogonal rotation. And whenever it is not required that the rotated factors will be orthogonal from each other, then it is called as oblique rotation. Just try to see this particular figure. This is called as orthogonal rotation. This is called as orthogonal rotation because once you see the rotated factor 1 and this rotated factor 2, there we can see that this is 90-degree angle is there. These two rotated factors are orthogonal to each other. So this is called as orthogonal rotation. The second type is oblique factor rotation. You can see the oblique rotation factor 1 and the oblique rotation factor 2, and you can see that these two are not orthogonal. So oblique type of rotation is there and other one is orthogonal type of rotation is there. So it depends on the situation, the context, the study, the investigation, the objective of the study, that which type of rotations we are going to perform. So I told you that these rotations are of two types. One is orthogonal type and other is oblique type. So whenever you do use some softwares, SPSS or some other analytical software, then there are different approaches to orthogonal rotation. One is called as Quantimax, other is called Varimax, and the third one is called as Equamax. So what is Quantimax rotation? So Quantimax rotation basically tries to minimize the number of factors which are loading to each variable. I will briefly explain, it is not required, otherwise my presentation will become very much complex, but I will try to simply, just in simple words, I will try to explain. Whereas in Varimax rotation, we try to minimize those variables which are responsible for cross-loading with different factors. And Equamax is a combination of Quantimax and Varimax. So these three approaches of rotations are there by which you can get the factors with clear picture from which we can go for clear interpretation of our factors. So in the second type, oblique type of rotation, again two methods are there. Direct oblique method is there and Promax method is there. I'm not going to explain them, but these two methods are also use. Basically, whenever you are using SPSS, we go for Varimax method, and that is the most common method of rotation. So I have discussed about rotation. Basically, rotation is done so that our results will be more clear. We can interpret in better way. It is basically done to maximize the higher factor loadings and minimize the lower factor loading, so that those variables which are cross loading to different factors, those variables which are uh, or those factors which are in common or seems common in different sets of variable, that things can be minimized, and we can see clear factor loadings of different variables, significant factor loadings of different variables on a particular set of factor or particular factor. Or we can see orthogonal, or you can get orthogonal factors or clear pictures, or we can interpret the factors in better way, we can name the factors in better way, we can analyze the factor in better way. It is just like observing a microorganism under a microscope. So whenever a specimen or slide is put inside a microscope, you must have seen, you are able to see that particular things without rotation also, or without adjustment of microscope handle or the adjustment equipments. Without adjustment also we can see, but if you go for adjusting the lenses or adjustment, then you will get the clear pictures. So in the same way, and will determine the specific organs of that microorganism. Similarly, here also through factor rotation, using different factor rotation, we can get the clear picture. Our interpretation will be simpler, our explanation will be simpler, and we can generalize our findings in better or suitable way. So that's why we go for factor rotation. So after understanding the different key terms related to factor analysis, like eigenvalue, like commonality, like correlational matrix, now we are in the position to see the next stages of factor analysis, or the remaining stages of factor analysis. So in the next stage, we can see that we have to go for constructing the correlational matrix. So once we construct the correlational matrix, we can visualize the relationship between the variables, which variables are highly correlated, which variables can be clubbed together, if there is sufficient degree of relationship is there, so that we can extract factors. So the correlation matrix will give you different types of ideas by which we can decide on further steps of factor analysis. In the next stage, we can decide on method of factoring. I told you there are several methods of factoring, like principal component analysis, like principal factor analysis, or common factor analysis, canonical factor analysis, image factoring. So there are different methods of factoring are there. The most common one is principal component analysis and common factor analysis. As I already explained you, the component analysis or principal component analysis is based on taking into consideration the unique variance as well as common variance as well as error variance, and just try to extract those factors which is responsible for maximum variance in that set of variables, in the set of factors. So first you extract those factors which are responsible for maximum variance, and then we go for the second cycle and continue like that. We extract those factors which are responsible for causing maximum variance in that particular data set. Secondly, in the factor analysis method or common factor method or principal axis method, we try to get the underlying factors. We try to, it is based on common variance, so we try to get those set of factors which are the underlying constructs, or which are latent, which are causing the maximum variance or which are causing the variance in that particular data set. So it is based on common variance and the other one is based on total variance. So that's why we have named it also. First one is component factor analysis. So we try to get the component. We just try to reduce the variable. But in the second one, we try to exactly get the factor. So whatever our objective of study is there, what is our requirement if you are going to see the underlying construct, you have to extract the factors, then you have to go for common factor analysis. Otherwise we'll simply go for principal component analysis, and both the methods are used while doing factor analysis, and these are most common one. So after this step, what we have to do, so next we have to determine the numbers of factors to be extracted. So next we have to decide the number of factors we have to extract. Now to extract this factor, there are certain criteria. Basically, we are trying to extract, I already told you that we need to extract those minimum number of factors which are responsible for most of the variance for that particular data set. Now there are different type of criteria which I will discuss in the later part of this video. What is the extraction criteria? So that we have to determine. So once we have determined that number of factors, this number of factors we have to extract based on eigenvalue, based on other criteria like scree plot, like eigenvalue, then we can go to the next step. The next step is the rotation step. So again we rotate the factors so that we can see the clear picture. We can see that which variable is loading to which factor, and we can interpret our result in better way. So rotation of factors is the next step. I told you there are orthogonal rotation is there, oblique rotation is there, using Varimax method, Promax method, Quantimax method, whatever method you can use based upon the objective of your study. You can go for rotation. You can see the exact loadings of variables for a particular factor. So through factor rotation, we can always minimize the cross loadings of variables, cross loadings of factors for different variables, so we can get a clear view. So rotation is the next step that we follow. Next, in the last step, we go for interpretation of factors. So once we get the clear picture, once we have extracted the factors, we can always go to interpret that particular factors. We can name those factors. We can give interpretation or explanation to those factors based on from which variables they have been derived. So based on the characteristics of those variables, the construct of those variables, that those factors can be explained. So interpretation is the last step of factor analysis. So we have reduced the variables to certain factors, and those factors in terms can lead to our explanation, our understanding to that particular data set or that particular behavior or that particular variables under investigation. So later on we can go for regression analysis to derive certain relationship, causal relationship in between these variables. So once we reduce the number of variables, we can always go for finding out regression and other things. So this is the last stage of factor analysis. So as I told you that I will be discussing on different extraction criteria for determining the factors. So now I will be explaining that one. So the first criteria for extraction of factor is based on eigenvalues. So I told you that those factors whose eigenvalue is 1 or more than 1, those factors should be only retained. Now what is the actual meaning of that one? So if you get a factor eigenvalue 1 or more than 1, it says that, or you can say that that particular factor is somehow in a position to better explain the situation or that data set than a single variable. That means eigenvalue of 1 signifies that that particular factor is sufficient enough to explain that particular data set or that variable if it is 1. So you can say that it is the variance is 100% for that particular factors in determining the data set. So we can say that if it is one or more than one, then it is somehow better in a better position than that single variable or set of variables in determining that particular construct or concept under investigation. So that's why we take the eigenvalues more than one. Now the second criteria is based on scree plot. As I already told you what is a scree plot. So scree plot, you have, it is quite obvious. It is based on eigenvalues. So whenever we see the elbow of that particular scree plot, whenever there is point of inflection from that point, above that point, all the factors can be retained. That after that particular point, the curve flattens, and that's why, and that eigenvalue is also less than 1. So you can clearly see from that scree plot, from that cut point, from that point of bend, or that point of inflection, at that particular point, you can decide above that point, you can take all the factors, retain those factors. So based on that scree plot, you can retain that number of factors. The third criteria is based on percentage of variance explained by the extracted factors. So it is, let me again make you understand. I have briefly explained this one earlier also, but let me again explain. So suppose you have extracted 2 factors or 3 factors. So if these 3 factors are capable of explaining the entire concept or variable under investigation. Suppose we have the combined variance of these factors is 70% or more than 70%. We can say that the variance which is obtained or which is produced by this set of factors is quite sufficient to determine the variance in the entire set of variable. If this value is less than 50%, 40%, it is quite obvious that we are not capable of finding out the factors, or we have not got sufficient number of factors which can explain that particular variable. So it should be around 70%. Now again, you just try to understand if this variance is very much close to 100%, 90% or 95%, that is also not a desirable position. That means whatever model we are going to produce, it is overfitted. It is actually not doing factor analysis, or it is a single factor model, or you can say that there should not be a high percentage of variance, very high percentage of variance explained by the factors. So that is also not a desirable position. So you have to be in between 70 and more. So you are in best position to get the desired number of factors. So you can always understand this position by looking at this particular figure. You can see in this particular diagram, which I have already explained, the component 1 is giving 37%, 37.3% variance. Component 2 is giving 18.6% variance, and component 3 is giving 11.3% variance. So if these 3 variants can be added, you will get a figure around 65 to 70. And I think it is quite sufficient to say that we have extracted the factors from this model. We have got the best model, or you can say that this is the variance explained by these factors are sufficient. We are successful in extracting the factors. So our extraction criteria is in between 70 to 80. It should not be very high, and it should not be very low, less than 50%. So I think you can understand what are the different extraction criteria on deciding the number of factors to extract. So in the final step of exploratory factor analysis, I told you that we go for interpretation of the factors. But if it is exploratory factor analysis, we have to name those factors also. So naming of those factors should be based on the variables from which it has been derived. Suppose, for example, for assessing athletic competency of an individual. Suppose we are trying to develop a tool, so we construct different questions on that particular tool, and our questions are like the height of the person, the weight of the person, the confidence of the person, the self-belief of the person, the age of the person, then the previous achievement. So different questions we can construct, and once we go to the field and collect data from the students while constructing that particular tool, we can see that when we go for factor analysis, we can see that we can get certain high correlation among certain set of variables which share common variance. Suppose some of the questions are quite related to the physical feature of that particular individual, like height, weight, age, like this thing. And some of the factors, like some of the variables like his interest, his confidence, his attitude, these all things can be related to his psychological aspects. So once we got this, once we go for item analysis, once we go for construction of the tool and go for analyzing the data set and conducting factor analysis, we can see that these items which are related to their physical feature can are yielding a factor, separate factor, and the features which are related to his psychological factors are yielding a factor, separate factor. So these particular items, when we can see, we can name that factor as first factor as the physical aspect of the individual. Second one can be named as psychological aspect of the individual. So this way we are actually the naming, we are giving the name of the factors. So based on the variables under investigation, we can always give name. We can also take into consideration the amount of factor loading each of the variable is responsible for in that particular factor. Let us take one more example. Suppose we are going to buy a car, and suppose a car manufacturing companies are there, then it is trying to analyze what is the criteria, preference criteria for the car, for deciding on which car the customer will buy. Then he has developed one questionnaire. Some questions may be related to the color of the car, the size of the wheel, number of seats. This is fuel. This one, fuel capacity. So this type of items can be there. Again, second type of items can be there. Cost price of that particular car, sale and resale value of the car. So this type of items can be there, and the other type can be there, that brand value of that particular company, or the previous record of that particular company of that, or we can say, or it can be the brand name, it can be the number of years of its services in that particular country. So we can construct different items. And once we go in the field and we can collect the data and go for factor analysis, we can always see certain correlation existing between the items, which like the size of the car, the color of the car. They may be clubbed together to give a factor like physical aspect of the car. Again, second one be this one, cost of the car, resale value of the car. They can be clubbed together to give a factor as the cost index, really cost issues, or cost aspect of the car, or price related criteria. So we can get different factors based on the variables which are being correlated, or which are yielding a factor. So based on those variables which are giving you a factor, we can give the name of the factors. So I hope, this being a very long video, you can always pause, you can always repeat the video, and you can try to understand it in if you play it you can always replay it, you can repeat it time, you can watch it. I have tried to give you a theoretical understanding of what is actually factor analysis. I have given you certain key term related to factor analysis, what is the meaning of factor analysis, what are the different uh, key concept related to factor analysis. So I think you are in certain position to understand what is factor analysis. Factor analysis has got different uses whenever we are constructing the tool, whenever we are trying to find out latent factors underlying different set of variables. So after this video, I will try to make a video or give a video on which you can understand how we perform factor analysis using SPSS, because I already told you that doing it manually is not a simple task, or it will take lots of time, lots of chances of committing mistakes will be there, lots of calculations are there, and simple, if you are not belonging to field of mathematics or statistics, you cannot simply do it. So better we can use certain statistical packages like SPSS or R. So I will try to make a video using SPSS and give you an example that how we perform factor analysis. By that, you will be able to do factor analysis whenever you will be doing some study involving several variables, whenever you are going to construct a tool, so you can do factor analysis. I hope this video, the theoretical aspects will always help you to understand that, but practical aspect also. Just mechanically doing the steps in SPSS without understanding what is factor analysis, it is meaningless. So I hope these two videos, this video and the previous video, will make you understand the basic of factor analysis, and in the coming video we'll understand how we do factor analysis using SPSS. So I hope you have understood this particular video, you have understood the basic ideas of factor analysis. So please subscribe to this channel and press the notification button also. Thank you.